Hello everyone, welcome to the solution of LeetCode problem 51 named n queens. In this problem, we are given a chessboard of size n by n and we have to place n queens into the chessboard such that no two queens can attack each other. Here, we are given an integer n and we have to return all distinct solutions to the n queen puzzle. And fortunately, we can return the result in any order we can. Now let's understand the first example. Here, n is equal to 4 is given. That means the dimension of our chessboard is 4 by 4. And we can place 4 queens here. At first, if we place the first queen here, we have to place the second queen in the last position of the second row. Because by placing this queen, both of the queen will not attack each other. And we have to place the third queen in the first position of the third row. And also we have to place the fourth queen in the third position of the fourth row. So by placing the queen in this formation, we can ensure that no queen can attack each other. Anyways, for a chessboard dimension 4 and 4, there is an alternative solution as well, which is this. So we can say that for n is equal to 4, there are two valid chessboard. So we are returning two valid chessboard here. One is this and another is this. Anyways, I am explaining the working procedure of this placement of the queen graphically in the next section. At first, we have to understand the working procedure of the queen placement. If we place any queen in a cell, then we cannot place any other queen in the same row, in the same column, in the same positive diagonal, and in the same negative diagonal as well. So we can say that a queen can attack the cell if the cell presented in the same row, in the same column, in the same positive diagonal. I am considering this as the positive diagonal because the slope of this diagonal is positive, and for the negative diagonal as well. So we can say that for each queen, we have to check 4 conditions. If we place any queen in a cell, we cannot place any other queen in the same row, in the same column, in the same positive diagonal, and as well as in the same negative diagonal as well. Now, at first, if we place our first queen into this position, we have to place our second queen in the second row because it doesn't make any sense if we place the second queen into the same row as well, because in this case, they will attack each other. Now, we have to check 4 conditions to place the second queen. At first, we have to ensure we should not place the queen into the same row. So, for this, we have to recursively call the callback function from the next row. And for the second condition, we have to check we should not place the second queen into the same column. So we have to place the second queen into the next column. By using this, we can ensure the first 2 conditions. Now, in the third condition, we have to ensure that we should not place any queen into the positive diagonal. So in this case, we have to check the positive diagonals as well. So how can we do that? There is a simple way to check the positive diagonal. Suppose this is our positive diagonal. And for this positive diagonal, we have to check the value of row plus column. Now, for this position, the value of row plus column is 3 plus 0, which is 3. For this position, the value of row plus column is 2 plus 1 is equal to 3. Now, for this, the row plus column is 1 plus 2 is equal to 3. And for this, the row plus column is 0 plus 3 is equal to 3. And for the clarity, we have to check one more positive diagonal. Here, for this, the row plus column is 3 plus 1 is equal to 4. For this, the row plus column is 2 plus 2 is equal to 4. And for this, the row plus column is 1 plus 3 is equal to 4. So we can say that all the value presented in the positive diagonal, which is row plus column, is same for each of the diagonal. So for a queen, we should not place any other queen in the cell for which the r plus c is equal to 3 or 4. So by using the value r plus c, we can find all of the positive diagonals. Anyways, let's see how can we find the negative diagonal as well. Suppose the negative diagonals are this. Because the slope of this diagonal is negative, so we can consider it as a negative diagonal. Now, for the negative diagonal, we have to check the value of row minus column. For the first cell, the row minus column is 0 minus 0, which is 0. For this, the row minus column is 1 minus 1 is equal to 0. For this, the row minus column is 2 minus 2 is equal to 0. For this, row minus column is 3 minus 3 is equal to 0. Again, for this cell, row minus column is 0 minus 1 is equal to minus 1. For this, the row minus column is 1 minus 2 is equal to minus 1. For this, the row minus column is 2 minus 3 is equal to minus 1. Again, for this diagonal, the row minus column for this value is 0 minus 2, which is minus 2. And for this, the row minus column is 1 minus 3, which is minus 2. So we clearly see that for each negative diagonal, the values of row minus column are same. So we should not place our second queen in any cell where the value of r minus c is exactly equal to the value of r minus c of the first queen. So by ensuring this logic, we can eliminate the negative diagonals as well. So finally, we can say that at first, we should not place our queen into the same row, and we will check this condition by using the row number. Secondly, we should not place our second queen into the same column. For this, we will check the column number. Thirdly, we should not place our queen into the same diagonal or into the same positive diagonal. For this, we have to check the value of r plus c or the row plus column. And for the fourth condition, we should not place our queen into the same negative diagonal as well. And for this, we have to check the value of row minus column. Now, let's try to put all of the 4 queen into the chessboard by using this 4 condition. Suppose at first we place our queen into the second cell of the first row here. So for this queen, we cannot put any other queen in this position, this position, this position, this position, and so on. So we can say that for the first queen, all of this marked position is prohibited for the next queen. So we have to place the next queen into the second row. So we can place it here, because by placing the second queen here, both of the first and second queen will not attack each other. And again, for the second queen, we cannot place any other queen in this position as well, and this position as well. Now, we can place the third queen into the third row here. If we place the third queen here, these 3 queens cannot attack each other, but we have to prohibit this cell for the next queen, because if we put any queen here, this will attack each other. Now, for the fourth queen, we have remaining only one place, which is this. And by placing the fourth queen here, all of these 4 queens cannot attack each other. So this is a one possible formation. And there is also another possible formation which is mentioned in the question. So anyways, I hope you understood what is the working procedure of this program. Now let's explore the decision tree. Suppose at first we are presented in the first row. For the first row, we have 4 choices. Either I can place in the first position, in the second position, in the third position, or in the fourth position as well. Now, for each of the position, we have another 4 choice. So I am not exploring the entire decision tree right now. I hope you understood the working procedure of the decision tree and also the mechanism of placement of the queen into the chessboard and the mechanism in which we are checking 4 conditions before placing a queen. So now I hope you understood the algorithm. Now let's move on to the code. In this code, at first we are given a function named solve queens. It has only one parameter, which is n. The dimension of this chessboard is n by n, and we have to take a vector of strings which will store the result. And at first we have to fill all of the chessboard of dimension n by n with the dot. Dot means empty cell. It does not contain any other queen right now. Then we have to call a backtracking function. The first parameter of this backtracking function is n, which is the dimension. The second parameter of this backtracking function is the row number. So at first, we are starting our backtracking algorithm from the first row. As we are using the zero-based index, so we are placing 0 here. The third parameter of this backtracking function is our result vector. And the fourth parameter of our backtracking function is our default chessboard, which is empty. And we have to consider 3 sets. The name of this set are columns, negative diagonals, and positive diagonals. These 3 sets will contain the value for the same column, for the same negative diagonal, and for the same positive diagonal as well. Anyways, in the backtracking algorithm, first we have to check either our current row is equal to n or not. If our current row is n, then obviously we have reached the base condition. Then we have to insert our current chessboard into the result vector. So we are doing it here. Now, for each column from 0 to n, we have to check either our current column is presented in the column set, or row minus column is presented in the negative diagonal set, or row plus column is presented in the positive diagonal set. If any of the condition is true, that means we cannot place our current queen here. So we will simply continue. Otherwise, we have to insert the value of column, row minus column, and row plus column into the corresponding sets, and we have to place our queen here, which is board of row column is equal to q. And after placing the queen, we have to recursively call our backtracking function from the next row, which is row plus 1. And we have also another choice. We can completely ignore the current position. So for this, we have to make empty our corresponding sets and put the value of dot into the corresponding chessboard as well. And finally, we will return the result. And this result will contain the all possible chessboard. I hope you understood the code. Thank you everyone for watching this video. We will get back soon with another LeetCode solution.